If you were to walk outside tonight and just look up at a clear, dark sky, right?
Mm-hmm.
And you just pick out any star, you would actually be looking at this profound mystery that stumped humanity for, well, almost all of our history.
Oh, absolutely.
Like the absolute smartest minds on Earth could not tell you if that specific star had worlds orbiting around it. I mean, we had our own little family of planets in our solar system, ones you can actually see wandering across our own sky. But beyond that,
Just a giant cosmic question mark.
exact, just a blank space.
Yeah, for centuries we were effectively blind to what was really up there. I mean, the idea that other stars had planets was a reasonable guess, a logical assumption.
Sure, it makes sense mathematically.
Right, but a guess is all it was. So the mission for our deep dive today is to really unpack this incredible paradigm shift. We're looking at a collection of astronomical data and some fascinating historical research that details how humanity went from knowing just a handful of planets to discovering over 5,000 of them.
In a single lifetime. That's the crazy part.
Yeah, in one lifetime. And maybe more importantly for you listening, we want to understand the incredibly clever, honestly, kind of everyday physics we use to actually find them.
The timeline of this is what absolutely blows my mind. Because the very first confirmed planet around an ordinary sun-like star wasn't found until 1995.
Just the blink of an eye ago in historical terms.
Right. Think about that. If you are listening to this right now, there is a very good chance that when you were in school, the only known planets in the entire universe were the ones right here in our own backyard.
Yeah.
And now, we're finding new ones faster than we can even name them.
We really are. But to appreciate how we got here, we kind of have to understand why we were stuck at 0 confirmed exoplanets for so long.
And exoplanets, that's just the scientific term for planets orbiting other stars.
Exactly, exoplanets. And the core problem of finding them is just a massive matter of scale and contrast. I mean, a star is trillions of kilometers away, and a planet, well, doesn't shine with its own light.
Right, it only reflects the light of its star.
Exactly, which makes a planet millions, sometimes literally billions, of times fainter than the star it orbits.
One of the researchers we're profiling today uses this beautiful analogy to ground the science, and I love this. He said, looking for a planet is like trying to spot a single firefly sitting right next to a lighthouse.
Yes, that's the perfect way to picture it.
But not just that. A firefly next to a lighthouse from the other side of a city.
Right, you just can't see it. The glare of the lighthouse completely washes out the tiny flicker of the firefly.
So if we can't see the firefly, how do we know it's there?
Well, astronomers realize that if we can't see the firefly, we have to stop looking for the firefly.
Okay.
Instead, we have to look for what the firefly does to the lighthouse. We look at the star itself.
Oh, that's clever. And this brings up the first major breakthrough we need to talk about, right? Something called the transit method.
Yeah, the transit method. It's brilliant in its simplicity. Let's walk through the mechanics of it. Imagine a distant solar system where a planet's orbit is lined up perfectly edge-on to our view here on Earth.
Like completely flat to our line of sight.
Exactly flat. Because of that specific geometric alignment, once every orbit, that planet is going to pass directly in front of its star from our perspective.
Right.
And when it does, it blocks a tiny, tiny sliver of the star's light. The star dims, just slightly, and then it brightens again as the planet moves on.
So it's essentially a mini eclipse.
That is exactly what it is.
Yeah.
If you are watching a star patiently and you see its light dip by the exact same small amount at regular, predictable intervals, you've very likely caught a planet crossing its face.
And NASA built a whole telescope just for this, didn't they?
Yeah, the Kepler Space Telescope. It was designed specifically for this one trick. It launched into space and basically just stared at a single patch of sky containing 150,000 stars.
150,000 stars all at once.
Right, and it didn't blink. It used highly sensitive digital sensors. Imagine a massive, ultra-precise version of the camera chip in your smartphone, just patiently watching for these faint, repeating winks of light.
And from just a wink, we learn what?
A massive amount, actually. We extract so much information from that simple shadow. First, the size of the dip tells you how big the planet is.
So bigger shadow means bigger planet.
Right. A bigger planet, say something the size of Jupiter, is going to block way more light, creating a much deeper dip than a small rocky planet like Earth.
Makes perfect sense.
And second, the spacing between those dips tells you the length of the planet's year.
because that's how long it takes to orbit and come back around.
Exactly. If the star dims every 10 days, you know the planet takes 10 days to complete a full orbit.
Okay, wait, let's pause here. Let's unpack this,
Yep.
because this brings up a huge logical problem for me.
Okay, hit me.
Doesn't this trick rely on incredibly, impossibly lucky geometry? I mean, space is three-dimensional.
It is.
So if a distant solar system is tilted even slightly from our point of view, that planet is going to orbit like above or below the star from our perspective.
Yeah.
So it will never cross the star's face, it will never cast a shadow toward Earth, and Kepler would just be completely blind to it.
Right. You're entirely right. That is a massive limitation. The transit method only works for the small fraction of planetary systems that just happen, purely by chance, to be tilted edge on to Earth.
So what are the odds of that actually happening?
Pretty low. The probability of an Earth-like planet perfectly aligning to transit a Sun-like star is roughly 0.5%.
Half of 1%.
Yeah. So for every single planet we actually catch transiting, there are literally hundreds more out there that are totally hidden from us just because of our viewing angle.
Wow. Which honestly makes the numbers we're seeing even more staggering.
Exactly.
Because even with that massive limitation, this edge-on method is still responsible for the vast majority of all the exoplanets we have ever discovered.
It is. It just goes to show how crowded the galaxy must actually be. I mean, if you're finding thousands of planets using a method that only catches a fraction of a percent of them, the total number of worlds out there must be astronomical.
Pun intended.
Huh. Yes. Pun intended. It is a statistical goldmine. But you know, knowing a planet's physical size, its volume, that only gives us part of the picture.
Why is that?
Well, a giant puffy cloud of gas and a dense, solid cannonball of rock could theoretically cast the exact same size shadow, assuming they have the same diameter.
Oh, right, because a shadow just tells you how wide it is, not what's inside it.
Exactly. To know what a world is actually made of, we need to know how much stuff is inside it. We need its mass.
Okay, so if the shadow can't tell us how heavy a planet is, how do we weigh a world we can't even see?
We use gravity, and this requires correcting a very common misconception about how space actually works.
Let's do it. Yeah.
We usually say that a planet orbits a star, right? And we picture the star sitting perfectly still in the center while the planet does all the moving around it.
Yeah, that's what we're taught in elementary school.
Right, but physics tells us that's not quite right. Gravity pulls both ways. In reality, both the planet and the star orbit their shared center of mass. Astronomers call it the barycenter.
Okay, I was trying to visualize this when prepping for this deep dive, and it reminds me of this, like, really lopsided dance.
Oh, tell me.
So, picture a heavy adult holding hands with a small child, and the adult is spinning the child around in circles.
Okay, yeah.
The child is swinging out in a really wide, fast circle. But the adult isn't perfectly still either, right?
No, they can't be.
Exactly. To balance the weight of the child swinging around, the adult has to shift their footing. They end up leaning back and swaying in this tiny, tight, slow circle themselves.
That's a great analogy.
Thanks. So if you're watching from far away in the dark, you might not be able to see the small child at all. But if you see the heavy adult swaying in that rhythmic circular motion, you know for a fact that they are swinging someone around.
You nailed it. The star is the adult and the planet is the child. The star's movement is incredibly small compared to the planet's orbit. I mean, the star barely moves while the planet swings wide, but the star does physically move. It is tugged around by the planet's gravity.
So it wobbles.
Yes. In fact, this technique is officially called the radial velocity method, but more casually, everyone just calls it the wobble method.
But wait, how on earth do we see a star wobbling? Because if the star is just a speck of light trillions of kilometers away, it's not like we can see it swaying back and forth through a telescope.
Right, we can't see the motion directly. We don't look at the position of the star. We look at the light waves leaving the star.
Oh, interesting.
Yeah, so as the star wobbles in that tiny circle, half of the time it is moving slightly away from us, and half of the time it is wobbling slightly toward us.
Okay.
Think of light as a spring or a slinky traveling through space.
No.
When the star moves toward us, it compresses those light waves, squishing them together.
Like the Doppler effect.
Exactly like the Doppler effect. The same thing that makes an ambulance siren drop and titch as it speeds past you. But with light, compressed waves shift toward the blue end of the color spectrum. And when the star wobbles away from us, those light waves are stretched out, shifting the color toward the red end.
So the star is actually rhythmically changing color. Like blue, red, blue, red.
Very, very slightly, yes. And astronomers use incredibly sensitive instruments called spectrographs to measure this tiny color shift. When they see that rhythmic stretching and compressing of light, they know they've found an unseen planet yanking its star around.
That is wild.
It is. And crucially, just like the adult and the child in your dance analogy, a heavier child is going to make the adult sway much harder. So by measuring exactly how fast the star is wobbling, we can calculate the mass, the weight of the unseen planet.
Ah, so this is the grand synthesis of modern astronomy. You use the transit method, watching the shadow,
Huh.
to get the planet's volume.
Yes.
And then you use the wobble method, watching the color shift, to get the planet's mass.
You've got it. And once you have the volume and the mass, it's just basic division to get the density. And density is the key to everything.
Because density tells us what it's made of.
Exactly. It allows us to deduce if a distant world is a dense, rocky ball like Earth or Venus, or if it's a puffy, lightweight ball of gas like Jupiter or Saturn. From just a couple of very clever, very patient measurements of starlight, we can completely reconstruct the physical nature of a world we will never, ever visit.
Which is just incredible. So armed with these two methods, the shadow and the wobble astronomers turned these tools to the sky in the late 90s and early 2000s.
Yeah, that's when things really took off.
And the very first major discovery completely broke our scientific models, didn't it? Like, it threw the textbooks out the window.
It really did. Astronomers had naturally assumed that other solar systems would look somewhat like ours.
Right, why wouldn't they?
Exactly. You'd have small rocky planets on the inside near the star and big, cold gas giants on the outside, all moving in nice, orderly, slow orbits. But the earliest discoveries were a class of planets we now call hot Jupiters.
Hot Jupiters, meaning what exactly?
These are gas giants, often even bigger than our Jupiter, but they are whipping around their stars in a matter of days, not years, days.
Wow.
They are orbiting closer to their star than Mercury is to our sun. They are absolutely roasting.
But nobody predicted them. I mean, a gas giant that close to a star didn't make any sense based on how we thought planetary systems formed. Shouldn't the heat have just blown all the gas away?
That was the big mystery. Why were our models so wrong?
Yeah, why were they?
Well, the models weren't entirely wrong. Our perspective was just heavily skewed by selection bias. We found hot Jupiters first because they were simply the easiest things to spot.
Oh, I see.
Think about the two methods we just discussed. A massive giant planet is going to cause a massive, easy-to-see wobble in its star.
Right.
And a planet that is huge and orbits very fast, very close to its star, is going to cause deep, frequent dips in light that are very easy to catch with the transit method.
So they weren't necessarily the most common, they were just the most obvious.
Exactly. They were the loudest signals in the data. They showed up first simply because they were the low-hanging fruit.
That makes total sense. So as our technology improved, as we launched better space telescopes and wrote better software to filter out the noise, what happened?
Well, smaller, quieter worlds started to emerge from the data, and this is where we learn a mind-bending fact about our own place in the universe.
Hit me.
It turns out the most abundant type of planet in the galaxy, the actual quote-unquote normal out there, is a type of planet size somewhere between Earth and Neptune. Astronomers call them super-Earths or mini-Neptunes.
And what's truly wild about that discovery is that this is a type of planet that doesn't even exist in our own solar system.
Yeah, it's completely missing. We have small rocky planets like Earth and Mars, and we have huge gas giants like Jupiter and Saturn, but we completely lack this intermediate size.
Which is strange, right?
It is, yet it seems to be the standard model for the rest of the Milky Way. These could be massive rocky worlds, or they could be entirely covered in oceans hundreds of miles deep. We simply don't have a local example to study.
So we are the weird ones.
Yeah, pretty much.
When you zoom out and look at the big picture of these discoveries, the scale is just breathtaking.
It really is. The current best estimates, based on the thousands of planets we've found and extrapolating for the ones hiding from our transit view, suggest that planets actually outnumber stars in the Milky Way.
Let that sink in. Planets outnumber stars.
When you look up at the night sky, you are looking at a galaxy where rocky, roughly Earth-sized planets exist in the billions.
Billions. Which naturally leads to the ultimate question for anyone listening.
Yeah.
Could any of them support life?
Ah, the million-dollar question.
Right. And you see it in the news headlines all the time. Astronomers find Earth-sized planet in the habitable zone.
I see those all the time.
It sounds like we should pop champagne and pack our bags. We found Earth 2.0. But I really want to push back on that because the data we are reviewing shows that this term is incredibly misleading.
Yeah, the habitable zone is a very specific and I would say heavily misunderstood astronomical term.
People also call it the Goldilocks zone.
Right, the Goldilocks zone. It is defined simply as the band of orbits around a star where the temperature would allow liquid water to exist on a planet's surface.
So not too hot, not too cold.
Exactly. It's not so close to the star that all the water boils away into steam, and it's not so far away that all the water freezes solid into ice. It is, theoretically, just right.
Okay, but in the habitable zone does not mean habitable.
No, absolutely not.
Just look at our closest planetary neighbors, Venus and Mars. If you map out our sun's habitable zone, both Venus and Mars are actually inside it. They skirt the inner and outer edges.
Yep, they technically qualify.
But if you visit them, neither one is a tropical paradise with flowing rivers. I mean, Venus is a crushing toxic furnace with surface temperatures hot enough to melt lead.
And Mars is an irradiated frozen desert. Neither one has oceans of liquid water on its surface today.
Right. So why is that? Why does distance not guarantee a habitable surface?
Because whether a planet can actually hold on to liquid water depends on far, far more than just its distance from the star. It depends on whether the planet has an atmosphere to provide pressure. It depends on what specific greenhouse gases make up that atmosphere.
Which traps the heat.
Exactly. And it depends on whether the planet has a strong internal magnetic field to protect that atmosphere from being violently blown away by solar winds.
Like what happened to Mars.
Right, Mars lost its magnetic field and then lost its atmosphere. These are incredibly complex variables. And for exoplanets light years away, these are variables we usually cannot measure.
Right.
So the most important takeaway here is that the habitable zone just tells astronomers where to look. It does not guarantee what they will find.
Okay, so if distance doesn't guarantee a habitable surface, and we obviously can't send a probe because it would take tens of thousands of years to get there, how will we ever know if there's life? Are we just stuck guessing forever?
We are not. This is the really exciting part. We are actively writing the newest chapter of this science right now.
Okay, tell me more.
We are moving from just finding planets to actually analyzing the air they possess. And to do that, we go back to the transit method, the planet passing in front of the star.
The mini eclipse.
Right. If that planet happens to have an atmosphere, something magical happens during that transit. A tiny, tiny fraction of the starlight doesn't just get blocked by the solid rock. It actually filters through the glowing fringe of the planet's atmosphere on its way to our telescopes.
Oh, wow. So the starlight actually passes through the alien air.
Exactly. And as it does, the gases in that atmosphere interact with the light. Every chemical element absorbs very specific colors of light. They basically eat those specific colors.
Okay, so when the light finally reaches Earth,
when it reaches Earth, it has microscopic chunks missing from its rainbow. It's often described as a chemical barcode imprinted on the starlight.
a chemical barcode. I love that.
Yeah, and if you read that barcode, if you look at exactly which colors are missing, you can work out exactly what gases the atmosphere is made of. This is a process called spectroscopy.
And we are doing this right now.
We are. The James Webb Space Telescope, which is operating right now, is doing this for the first time with unprecedented precision. It uses massive gold-plated mirrors to catch that filtered starlight, and it is actively teasing out the barcodes for water vapor, carbon dioxide, and other molecules in the air of planets sitting trillions of miles away.
That is just incredible. But what are they actually looking for in that barcode? Because finding carbon dioxide doesn't mean aliens, right?
Right. The holy grail for astronomers is finding what's called a biosignature. The dream isn't just to find random gases, it's to find a very specific combination of gases.
Like what?
The major example scientists look for is finding oxygen sitting right alongside methane in the same atmosphere.
Oxygen and methane. Why those two specifically?
It all comes down to the mechanics of chemistry. Oxygen is a highly aggressive, highly reactive element. It is essentially an electron thief.
An electron thief, okay.
It desperately wants to bond with other elements. It wants to rust iron, it wants to burn carbon, and it desperately wants to react with methane to form carbon dioxide and water. Because oxygen is so chemically aggressive, oxygen and methane will naturally destroy each other in an atmosphere.
So they shouldn't naturally coexist for very long.
Exactly. Left alone, they wipe each other out.
Okay, so if we look at a distant planet and see a strong signal for both oxygen and methane,
And then it means something is actively, constantly pumping massive amounts of those gases back into the air faster than they can destroy each other.
oh wow.
It represents a massive, ongoing chemical imbalance, and on Earth, the primary thing maintaining that kind of extreme chemical imbalance is life.
Right, plants and bacteria are constantly pumping out oxygen and methane.
Exactly. Finding that imbalance on another world would heavily imply that something living is down there, breathing, metabolizing, and altering its environment.
So that chemical imbalance is the biosignature.
Yes. But we need to temper our expectations with a deep note of caution here.
Fair enough. Have we found one?
No, we have not found a biosignature yet. These measurements, filtering starlight through an alien atmosphere, are sitting at the absolute bleeding edge of what is physically possible with current technology.
I mean, a missing slice of color in a beam of light that has traveled for 50 years isn't exactly a slam dunk.
Not at all. The signals are incredibly faint and very easy to misread. It may take a very long time before we can definitively say we've found a biological chemical imbalance, and honestly, it's possible we may not find one in our lifetimes.
That's sobering.
It is, but the profound shift is this. For the very first time in human history, searching for alien life is a real, executable scientific experiment.
Rather than just a philosophical daydream.
Exactly. We are no longer just wondering, we are finally looking.
What a journey it has been to get here. I mean, within a single generation, within the span of a few decades, our understanding of the universe has been turned completely upside down. We went from a quiet, lonely family of 8 planets to discovering a galaxy that is literally teeming with worlds. Worlds that outnumber the stars themselves.
It's beautiful. And I think the most beautiful application of this knowledge is how it changes your everyday experience.
How so?
The next time you walk outside and look up at a point of light in the night sky, you don't have to wonder anymore. You can be fairly sure that you're looking at a sun with worlds of its own. By just patiently watching starlight flicker and shift color, we've realized that the sky is far more crowded and far more interesting than we ever knew.
That is amazing. And I want to leave you, the listener, with one final thought to mull over, building on what we discussed earlier about planet sizes. We just learned that the most common type of planet in our entire galaxy, the super-Earth or mini-Neptune, is completely missing from our own solar system.
Which still blows my mind.
Right? It makes you wonder if alien astronomers are pointing their own telescopes at our sun right now, looking for those familiar, quote-unquote, normal planets they see everywhere else. What assumptions might they be getting completely wrong about our unusual, quiet little family of 8?